Okay, well, let's begin then. Okay, hello everybody, and welcome to a new session of this webinar for differential geometry in South America. And today it is a great pleasure to have with us uh, M.Jablonski from the University of Oklahoma. And this time he will speak about non-compact real semi-simple algebras are determined by their Iwasawa subalgebras. Okay, Mike, thanks, and go ahead, please.
Great, thank you. Thanks for the invitation. It's nice to see, some friendly faces and some friendly names, that I haven't seen in several years. So many thanks for inviting me to speak. So I'm going to try to give a talk that's as close to a chalkboard talk that I can, just because that's the kind of talk that I enjoy giving. It'll be a little bit different. So if you see me moving my hands a lot, don't hesitate to ask me to draw more, and I'll do my best. So the theorem that I want to talk about is new as far as I know, but it's kind of surprising. Surely some people must have known this before. I'll state it at the Lie algebra level. You could state it at the group level, but here it is. Let G1 and G2 be real semi-simple Lie algebras of non-compact type, and I'll remind everyone what this means in a little bit. And then I want to consider their Iwasawa subalgebras. I'll remind everyone the definition of this later in just a moment. So let S1 and S2 be the Iwasawa subalgebras of G1 and G2, respectively. If S1 is isomorphic to S2, then G1 is isomorphic to G2. So this is the main theorem, and then even further. So furthermore, the isomorphism is the restriction of an isomorphism between the semi-simple objects. So this is the main theorem. The proof's not very long. I'll give the proof closer to the end. Before doing that, I'll remind everyone why semi-simple Lie algebras and Lie groups are interesting. But if you want to have some examples in mind, maybe I should give you some examples. So maybe take like G equals SL and R. This is a real Lie algebra that's of non-compact type. And here the Iwasawa algebra is just going to be the upper triangular matrices. Obviously inside of SL. So maybe I should say of trace zero. Okay, so some motivation for why people are interested in semi-simple Lie algebras. So algebraic interests. Well, first, simply connected Lie groups. Correspond to their Lie algebras. So anything I want to say about Lie groups, I can roughly understand in terms of its Lie algebra. Here's a definition. We say G is simple if 1, it is non-abelian. So it's a choice I'm making. And then 2, G has no proper ideals. So for example, I don't know, like SON, right? So for n greater than or equal to 5. Okay. Just a few quick definitions to remind everyone. Definition: we say G is semi-simple if the killing form is non-degenerate. So the killing form, what is this? So this is a natural bilinear form on the Lie algebra. So if I have some element x in the Lie algebra, then I have add x, which is a map from G to G, and then the killing form is the bilinear form, the symmetric bilinear form, where I take the trace of add x composed with add y. So, and if this is non-degenerate, then you say the Lie algebra is semi-simple. So there's a well-known theorem, fundamental theorem, that says G semi-simple if and only if it can be decomposed into a sum of simple ideals. And then there's another well-known theorem. So let G be a Lie group with Lie algebra G. Then G is compact semi-simple if and only if the killing form is negative definite. So it's interesting because you can detect this topological feature of compactness just by working at the Lie algebra level and computing this symmetric bilinear form. So now I'll give a definition of non-compact type. So we say G is non-compact type if none of its simple ideals is compact. And again, that's something we can detect purely at the Lie algebra level using the killing form. So just to contrast this a little bit, just contrasting with the other extreme, one could consider nilpotent Lie algebras. And here the killing form is identically 0. So semi-simple and nilpotent objects are kind of the two extremes for Lie algebras. And you might recall from a basic course in Lie theory that basic fact, just reminding people how all these parts fit together. Every Lie algebra is a semi-direct product. So I'm just saying it's built out of two fundamental pieces of a semi-simple and a solvable. All right. So fact, the complex semi-simple Lie algebras, they were classified in the late 1800s by Killing. So the complex semi-simple Lie algebras were classified by Killing in around 1890. That's modulo mistakes or issues in the proof. The proofs were apparently corrected by Cartan, who later classified real semi-simple objects also. Okay, so that's the algebraic motivation for thinking about semi-simple Lie algebras. Now I want to give a geometric motivation. So here's a fact: semi-simple Lie groups arise as the isometry groups of symmetric spaces. So just to remind people who don't think about these things, especially graduate students. So what is a symmetric space? Well, so here's what we'll do. We'll let MG be a Riemannian manifold. So I'll do my best sketch of a Riemannian manifold, something like this. And what I want to do is I want to define something called geodesic reflection. So what do? I take a point P, and I'm going to take some other point Q, and I want to define a reflection. So I'm going to look at the geodesic. So I'll have this geodesic gamma. So let gamma from 0 to 1 into M be the geodesic joining P and Q. So that is, so I'm setting this up so that at time 0 I'm at P, and at time 1 I'm at Q. Okay, so geodesic reflection is the map. So it's the reflection at P, so it's going to be the map sigma P, which eats Q and returns a gamma of -1. So I'm saying instead of going out in this direction, time 1, the reflection is back here at time -1. And then here we go. If sigma P is in the isometry group, then we call MG a symmetric space. So these are, well, if this is true for all points P. If this is true, so I should insert this for all points in the manifold. So let me give some examples. So the first example is Rn. So here I am in Rn. And because it's so easy, I'm going to calculate it. So I take a point P, I take some point Q, I take my geodesic between these, and then the reflection should be back here. So what is this point? So I need to know the line that goes through here, right? So this line would be, I guess, P plus T times Q minus P. And then what is sigma of P, sigma P of Q? This would be P minus this. So it's what, 2P minus Q. So you can see it's what? It's a composition of inverting, right? So sigma P is translation by 2P precomposed with minus the identity. And both of those are isometries of Rn. So there you go. So Rn is a symmetric space. Let me give you one more example. Again, because it's so easy, it's hard not to give the example. So if I take a sphere, and I'll just take my point to be the North Pole, So let me take a point, I don't know, Q right here, and we know what the geodesics are. These are the great circles, and I can realize that great circle just by taking the correct plane, the correct vertical plane, and slicing through the sphere. And so if I'm looking at this from above, so from above, right here is my point, which is the North Pole, and that's the equator, and then my point Q is somewhere right here. And so from above, you can see that you just follow that straight line. And so to get the geodesic reflection, I just follow the same straight line backwards. And I think everyone will believe, or at least give me the latitude to write this down. So in coordinates, if I took Q equals XYZ, then the geodesic reflection is just I reflect in the XY coordinates. And so if I write this down, it's minus the identity on the X and Y, and then a 1. And that's definitely an isometry of the sphere. And of course, if you had a general point, you do the exact same thing, right? Instead, you would just say, right, it would be minus the identity on the orthogonal space to P, and then just one the identity in the direction of P. Okay, so other quick examples, which I won't compute, but I'll just write down since they're familiar. I don't know how to draw hyperbolic space, but hyperbolic space, Grassmannians. So the Grassmann manifolds. One of my favorites, the space of inner products on Rn is naturally a symmetric space. So the important thing is this. There are a finite number in any dimension. And in my opinion, the compact ones are easier to describe. So I'll describe those real quick. So from my point of view, the non-compact, irreducible, are easier. So how do you describe these? Well, so fact, these are of the form G mod K, where G is non-compact and simple. And I'm gonna throw in the condition of linear. It's a small technical condition. You can throw it away just by quotienting by the center. So G is non-compact and simple, and then K is a maximal compact. And that's it. That's how you build all of these. And then if you wanted the compact ones, you could just do something that's called the dual procedure and easily build all the compact ones. Okay, so this is not the only transitive group on a symmetric space. So let me recall an example. If I took a hyperbolic space like H2, then oftentimes we write this as PSL2R mod SO2. But of course, there's another friendly group that acts transitively on this. So another transitive group of isometries. I could take the upper triangular matrices. And it's easy to see this acts transitively just because, well, in general, we have something called the Iwasawa decomposition. So let me remind everyone what this is. So the Iwasawa decomposition of a, well, I'll say non-compact. I mean, it's true for semi-simple in general. It just doesn't mean very much for a compact one. So the Iwasawa decomposition of a non-compact semi-simple Lie group. G is, well, it's this decomposition G equals KAN, where this K is a maximal compact. And yes, I know. So I'm being slightly dishonest. If the center of G is, in some cases, K might actually be non-compact, but I'll just stick with the lie because it's mostly true. So K is a maximal compact. N is some nilpotent group. This A is some abelian group. And then the A and the N you can fit together. So N is normalized. So let's just say it. N is normalized by A. But it's not necessarily normalized by K. So when I write this Iwasawa decomposition KAN, this is just a product as manifolds, but it's not a product as Lie groups. So, but we do get this. So we get S equals AN is a solvable subgroup. And in some kind of moral sense, it plays the role of the Borel in the real setting. So this is similar in a sense to the Borel subgroup of a complex semi-simple. All right, so maybe I should give you a couple of examples just so you have some toys in the back of your mind. Well, so I think I already said before, if G is SLNR, then you could take this, you can take N to be the upper triangular matrices with zeros on the diagonal. And then the A would be the diagonal matrices. If I took another example, if I took G to be, let's say, SO1N, then this S is a semi-direct product. So here the nilpotent part is abelian, and then the way that the A acts on it is by the identity. All right, so maybe I'll restate the main theorem and then give a sketch of the proof. So theorem, S is completely determined. Well, S completely determines G. Oh, so I'm writing this at the group level. So I'll say it like this. If G is of non-compact type and simply connected. So what does the proof of this look like? So the proof uses some tools from the geometry of solvmanifolds. So maybe first I should say what's a way to prove this? So a way to prove this would be to look at a classification list. you could you can list off all the the real simple Lie algebras of non-compact type in a certain dimension. This is a finite list. You could compute all of the data from the Iwasawa decomposition. You can compute the n, you can compute the a, and then you can take their semi-direct product to get this s. And you could look at this list, and then you could say, well, the s's that show up on this list, they aren't, they're distinct. So none of them coincide, and therefore the s tells you the g. I don't know of anyone who's done this. I mean, I wouldn't be surprised if this is an observation that people have made at some point. But somehow this isn't a satisfying proof because it relies on a classification list. Even if the classification is good and well known, it's still somehow not the satisfying proof. So we'll give a geometric proof. So here's what you do. So what do we have? We have S acts on G mod K, and so picks up a left invariant symmetric metric. We know that every symmetric space can be written as a product of irreducible symmetric spaces, and each irreducible symmetric space is Einstein, and so we can tweak this. So we can tweak so that the choice of symmetric metric is Einstein. Okay, so a fact about Einstein metrics. So this is due to Jens Haber from 1998 and a work by Jorge Laurette from 2010. Einstein metrics on solvmanifolds are unique up to isometry and scaling. And so that's what we're going to take advantage of. So here we go. So let's consider an isomorphism. So maybe I'll call it psi. It goes from S1 to S2. And then what I'll do is I'll pull back the Einstein metric from S2 to S1. And then what I have is now we have two Einstein metrics on S1. These have to be isometric. So these are isometric, which implies the isometry groups are isomorphic. And in particular, we have the connected component, or the connected isometry groups are isomorphic. That is, G1 is isomorphic to G2. So that's the idea. So use this uniqueness of Einstein geometry to get the isomorphism between the G's. So I should say this is not quite enough to get the last part of the theorem. So what was the last part of the theorem? So I'll say not quite enough to get that the isomorphism between the S's is induced by the isomorphism between the G's. So the reason it's not quite enough is, so when you have this isomorphism between the G's, if you pull back the S2 using the isomorphism, you get two different Iwasawa groups inside of G1, and you know these are conjugate, but it's not quite enough to get what you want. So to prove this part, you have to use more results. So maybe at the end, if someone asks a question, I'll say more about it. So I'll just say this for now. To finish, one needs to use some facts about Einstein solved manifolds having so-called maximal symmetry. Okay, let me give an example. I want to compare the real setting to the complex setting. So maybe I'll ask this question: Is the result really surprising? And the reason I ask that is, I said that the Iwasawa, so the Iwasawa of a real semi-simple, is, plays the role of the Borel subalgebra for a complex semi-simple. So if you take the Borel subalgebra of a complex semi-simple, so what can you extract? So given a Borel subalgebra, you can recover the Dinkin diagram, and from the Dinkin diagram, of course, you can recover the original semi-simple. And so you might say that you want to try the same idea in the real setting. So in fact, you can get rid of the Borel up here, and you can replace that with the nilpotent part. So you can say the nil radical of the Borel. So if you take the nil radical of the Borel, you can actually recover the Dinkin diagram, and so the original semi-simple. So I should say this picture does not work in the real setting. And actually, this is the question actually that got Jon Epstein and I working on this project is, for whatever reason, we were studying these nilpotent parts of real semi-simple algebras, and we wanted to know if that determined a real semi-simple, and the answer is it does not. So here's an example. So maybe I'll write the question first. So question: Does N from the Iwasawa decomposition determine G? And the answer is no. Okay, so here's the example. I could take N to be the Heisenberg, the 3x3 Heisenberg Lie algebra. So this is at the Lie algebra level. I've got to make sure I don't write too many zeros. So it's just this algebra of matrices. So the upper triangular. And this appears for both G equals SL3R, and it appears for G equals SU21. So maybe, by the way, this talk goes way faster when you're writing on an iPad. On a chalkboard, I would, it takes maybe 20% slower. So I'm almost done. Maybe I'll ask a question. It's one of the questions that's motivated, some of what I talked about today. So if I take this Iwasawa subalgebra S plus an, and what I can do is I can say there's a special element. S contains a special element called the pre-Einstein derivation. So I'll call it D, and there's a fact. Let A bar be a subspace of A. Then A bar semi-direct product N has a Lie group S. I'll write it like this, which admits an Einstein metric. If and only if D is contained in that subspace. And so, I definitely have, well, so here's one thing we can do. We can build this subalgebra. It sits inside of here. And so for some other reason, we were interested in this question. Which of these admit symmetric metrics? And so I'm being very casual in the way I say this. What I really mean is I take this the algebra, and really I want to look at its corresponding Lie group. So which of these S, maybe I'll call it S bar, admit symmetric metrics? And what you might hope for is that there's a unique one, but it turns out this isn't the case, at least not when you take N as the Heisenberg, the three-dimensional Heisenberg. There you get these two different subspaces which admit these symmetric metrics. So this is a question that we're interested in, and we still don't have an answer to. So if anyone's thought about this, I'd be interested to hear your thoughts. All right, I'll stop here early because it's not a chalkboard talk. It was all on my iPad. Thank you.
Okay. Thank you very much, Mike, for this very nice talk. We can, with the reactions here,
Thank you.
It's easier than to look for the clapping. So, are there any questions? Maybe Diego Conti?
Sorry, we'll just try to clap. Let's talk.
Okay. Thank you. So, are there any questions or comments for Mike? So, well, maybe I can ask, what happens with the case of the non-compact semi-simple Lie group, but which is not of non-compact type?
Which is if it's good question. I should have said this. So let me show you. I'll give you an example.
Yes.
Right, so if I just take G1 is compact simple.
Yes.
And I take G2 is non-compact simple. And then for the G2, if I write this, the Iwasawa decomposition like this, then for the sum of these, the Iwasawa decomposition is just the G1 plus the K1 plus the A plus 1. And so you can't, right, if all you're looking at is the A plus N, then you'll never see those factors which are compact.
Okay. I see. That's good. And and how did you use this hypothesis of being of non-compact type in the proof? I don't recall that.
Oh, well, it's really so that if you look at G mod K, you want the G acting effectively,
Yes.
because that tells you that G is the isometry. Well, roughly, right? So that I'm going to assume G is
Yes.
connected. So G is the connected component of the isometry group. So to get that, you need G acting effectively. And if G had any simple factors, they would just get absorbed into the K and disappear.
Okay. 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 Good. Right. Okay. Are there any other questions or comments for Michael?
Hi.
Well,
Hello. Hello, Adrian. Hi, Michael. Thank you for the talk. Are you hearing me?
I can hear you. Yeah, thank you.
Could you come back, please, to your question? I didn't understand very well what A bar is, because you have N and you have D, and then you ask for an A bar like intermediate with A. So you
Yeah.
want.
So, yeah. So what is this A bar? So A bar is some subspace of this A, and I want to consider the K. So let me write down here. So A bar.
That has a symmetric metric. Okay, I see.
Yeah.
So you have A plus A semi-direct N who has a symmetric metric, and then you want a smaller A bar.
Yeah. Yeah, exactly. Yeah. So we want to know if there's a smaller A bar that also has a symmetric metric.
But is it RD semi-direct N always admits symmetric metric?
It admits an Einstein metric. So in the case when N is the Heisenberg, then the answer is yes. So you end up with these two extremes that have a symmetric metric. I'll be honest, I haven't thought this much about it. It's the only example I know of. For two reasons. One, once I had the example, I lost a little bit of interest in the question for the reason that we were thinking about it. And two, we were computing something and we only had to deal with this one bag case. And so for our purposes, we didn't have to deal with any more cases. But the question was still kind of interesting to us. And so, normally I don't think you would expect this to have a symmetric metric. And I would say I'm pretty sure the only time it would have a symmetric metric should be this case where N is the Heisenberg. But again, I haven't spent more than 60 seconds thinking about it.
Okay, so in general, you don't know if such A bar actually, if there is a smaller A bar.
Right, yeah.
Okay, but that's a nice question. Interesting. Okay, thanks.
Okay. Are there any other questions? Well, if not, let's thank Michael again. And we are, thank you again for coming today. Thank you, Michael, for your very nice